representations of so-called rational functions. Okay? And rational functions are functions which are quotients of polynomials. So an example here, the bottom of page 28. This function here, x over this cubic, x cubed plus x squared, etc. That's a nice compact form of that expression, which could define a function of x. But on the right-hand side, after a couple of lines here, we have a different form, and this is called the partial fraction expansion. Okay? It represents the rational function as a sum of simpler rational functions. And they're regarded as being simpler than the original one because the denominators have lower degree. Okay? So there's a general method for finding these kind of things. And one place where these find use is in integration. So in order to integrate the original function, we can instead use standard results about how integrals of simple rational functions behave, and then use the decomposition of the original function into this collection of partial fractions to do the integration. Now the general method, and I think it's best illustrated by looking at some examples, but it relies on this fact here in 3.2 about the factorization of polynomials. So we discussed this yesterday morning. And this theorem, now we're not going to prove it by any means, but it kind of underlies this whole process. And this says that well, any normal, so this is a normalized polynomial of degree n. Normalized meaning that the coefficient on the x to the power n term is just 1. And then it has general coefficients on the later terms. So it's got an minus 1 times x to the n minus 1 and so on, all the way down to a constant coefficient of a0. Now, if the coefficients are all real numbers, then this theorem says you can factorize that p into a product of factors. And each of the factors will have, well, one of two types of forms. They will either be some power m of an x minus a term, or some power m of a quadratic term, x squared plus ax plus b. So you won't still see, you don't, every polynomial with real coefficients can be factored down into just products of factors of those types. Okay? And these give you how the denominators are going to look like in the partial fraction expansion. Okay? Now the general method is described there, but I'd rather investigate it with the use of these examples here. So now the examples are mostly set out there in the notes, but I'll just work through the first one at least by hand just to illustrate it and talk about it as we go. So this first rational function is 3x plus 1 over x cubed minus 3x plus 2. Okay. And so the first step we do is we obtain the factorization of the polynomial in the denominator. So in order to do that, we kind of have to locate the roots of the polynomial. So the roots of these are 1 and minus 2. So we know this polynomial is going to factorize the denominator polynomial is going to factorize like that. Okay. And then using the general method described on the previous page, such a rational function will have a partial fraction expansion which appears like this. We'll have some constant over x minus 1, some constant yet to be determined over x minus 1 all squared, and lastly a third constant over x plus 2. So each factor that appears in the denominator of the original rational function, we get a corresponding term in the partial fraction expansion. If the factor is just an x plus 2 on its own, like here, then you get a single fraction c over x plus 2. However, if it's a term like this, x minus something raised to some power, then you get one fraction for each of the increasing powers up to and including the total power there. So because this is just 2, we have something over x minus 1 and a something over x minus 1 all squared. So the a, b, and c are to be found. Okay. And we can find these, the way I like to talk about finding these is to immediately rewrite it back as a single fraction again. So you do that by expressing each of those fractions over the common denominator x minus 1 squared times x plus 2. And that will mean that your a is multiplying x minus 1 times x plus 2. The b has to multiply x plus 2. And the c has to multiply x minus 1 all of it squared. So we get this new expression for the original rational function. Now the denominators here are the same. And if the denominators in these two representations are the same, that means the numerators must be the same as well. Now this numerator we see as this simple polynomial 3x plus 1. Here we've got a general quadratic polynomial. So the way to find out what the a, b, and c are, the way I like to describe it is we first of all work out the standard expression for the numerator as a polynomial. So what's multiplying x squared in it? Well, there's an a times x squared and there's a c times x squared. So in total you've got a plus c times x squared. What's multiplying what's multiplying x? Well, what's multiplying x involving a? Well, involving a, you've got, in total, when you multiply these out here, you've got 2x minus x. You've got a minus x. So there's going to be minus a multiplying x. Then there's going to be b multiplying x from here. And minus 2c multiplying x in the third part. Then lastly, you look for what constants are around. Well, there's a constant minus 2a from the first part, a constant 2b from the second part, and lastly a constant, well, when you square that out, you get 1 as the constant term here, so there's a c in the constant term there. So that's multiplying x there. So there I've got the standard representation for a polynomial in the numerator here, something times x squared, something times x plus a constant. And then the principle here, this numerator polynomial must be the same, must have the same coefficients. And the only way two polynomial functions can be the same is if their coefficients agree of corresponding terms. So it must have the same coefficients as the original numerator. Which is 3x plus 1. So this gives you a system of equations. This coefficient here, a plus c, this must equal the coefficient of x squared that we had originally. Now we don't have an x squared originally, which means the coefficient is 0. Then the minus a plus b minus 2c, that must equal the coefficient of x we had before, so that's the 3. And then the constant coefficient we have down here, minus 2a plus 2b plus c, that must equal the constant coefficient we had originally at the top of the page. This constant coefficient 1 here. Well, this we recognize as a system of linear equations. In the three unknowns, a, b, and c, you've got 3 equations. So you're well aware from your linear algebra work that there's a standard method for solving equations like that. You can use a Gaussian elimination. If needed, if you can't solve it very quickly by substitution and so on, you can always use Gaussian elimination, or so it's also called row reduction algorithms to solve this system. Okay. Now you've been looking in the linear algebra unit how to do those. So you set up the augmented matrix. the augmented matrix is the coefficient matrix. We've got columns A, B, and C. The coefficient matrix looks like this: minus 1, 1, minus 2, minus 2, 2, 1. That's the coefficient matrix for columns A, B, and C. And then you have a fourth column, which is the column of constants on the other side of the equation. And then you row reduce this equation, as you've been looking at in the linear algebra unit. And when you row reduce this equation, you get, this will reduce to, this row reduces to the matrix, well, it will row reduce to a diagonal matrix in the coefficients. Sorry, 1, 1, 1 on the diagonals. And then the fourth column will look like 5/9, 4/3, 4/3, and the last one is minus 5/9. Okay, so we can read off from this then the solutions. A will be 5/9, B will be 4/3, and C will be minus 5/9. Okay. Is that okay? Any questions about that? So I skipped over the actual row reduction steps. We'll be covering that in the linear algebra unit. The second example there shows you how the irreducible quadratic factors are dealt with. So in this second example here, the rational function we're dealing with is 5x over x cubed minus x squared minus x minus 2. Now when we attempt to factorize that cubic, we find we can only factorize it down into the linear factor x minus 2 times the polynomial x squared plus x plus 1. Now that polynomial x squared plus x plus 1 is irreducible over the real numbers. It can't be factorized any further using real numbers as coefficients. Could if you allowed yourself to use complex. But just keeping everything real means you can't factorize it any further. But we can still find a partial fraction expansion. So we'll have something over x minus 2 and something over x squared plus x plus 1, except when the denominator is one of these irreducible quadratics, then the numerator that goes along with it has to be the general order 1 numerator. So a constant plus a constant. So some unknown coefficient plus unknown coefficient times x. So there's again 3 coefficients that we're looking for here: the alpha 1, beta, and the alpha 2. And we can find those by the same technique. Multiplying, bringing the sum of 2 fractions there, bringing it again to a single fraction over the original denominator. See that the numerator you end up on the right-hand side with is alpha 1 plus beta x times x minus 2 plus alpha 2 times the irreducible quadratic. That's the numerator, so that numerator polynomial will have to equal our original numerator, which was the 5x. And the only way that can happen, the only way that these 2 polynomials can be equal is if their corresponding coefficients are equal. So the total coefficient of x squared on the right-hand side will have to be 0, because there is no x squared on the left-hand side. The total coefficient of x on the right-hand side will have to equal 5. And the total constant coefficient on the right-hand side will have to equal 0, because there is no constant on the left-hand side. So again, you get a system of 3 equations and the 3 unknowns, alpha 1, beta, alpha 2. So you can use the Gaussian elimination technique to solve those if the solution doesn't immediately show itself by means of simple substitutions and so on. And we do have the Gaussian elimination algorithm, which will solve it for us. Okay. So that's some examples of the partial fraction expansion. The general method is described over on the previous page. And there's a few examples there, example problems in the end of chapter exercises for you to have a look at. Okay. Now these won't be appearing, none of this material from chapter 3 will be appearing in the class test at the end of this term. The class test at the end of this term is just everything on sequences and series, up to but not including the power series material. Okay. And the announcement to that effect is contained on the Moodle page.